Today we'll be talking about this expression, del cross del t is equal to 0, where we define t to be a scalar field. Scalar field. So what does it mean when we say del t? Well, this becomes the scalar field when applied with the operator del becomes a vector field. So we have partial t with respect to x, partial t with respect to y, and finally partial t with respect to z. And del by itself we define to be the partial derivative, and it's a vector operator, like so. So what does it mean for this expression? Well, in order to figure this out, to see if it actually does equal 0, we can use the determinant of a 3 by 3 matrix. In the first row, we have I, j, k, the unit vectors for x, y, and z. For our second column, we have the components of del, namely the partial with respect to x, with respect to y, and with respect to z. And for our last row, we have partial t with respect to x, with respect to y, and with respect to z. Now, as shown in the previous video, when we're evaluating this expression, we have I times the determinant of the remaining rows and columns. So we have del, the partial derivative with respect to y, with respect to z, and then when applied to t, we have the same, minus j, and once again we follow the same idea, except now with x and z. So x and z, and when applied to t. And finally we have k, our z unit vector, and we have x and y. X, y, and x and y with respect to t. Now, when we're evaluating this, let's first consider this determinant. We know that this is equal to partial y times partial t partial z minus partial z times partial t over partial y. Now, the order in which we take these operations of taking the partial derivative with respect to y and respect to z, the order doesn't matter, so these two are equivalent. So this whole thing goes to 0. And if we evaluate those for j and k, we find that they also end up being 0. So minus 0 plus 0. So the end result is that this entire expression of del cross del t, where t is a scalar field, is just going to give us 0.